It is February 1st, 2026. Somewhere over the South Pacific, a pilot is cruising at 38,000 feet, running a routine check on the radio. Static. Nothing but static. He switches frequencies. More static. He tries again. Silence. From where he's sitting, the sky is perfectly clear. No weather, no clouds, no explanation. He has no idea that 93 million miles away, the sun just detonated one of the most violent explosions in the solar system. And that explosion is already here. That moment, that eerie, unexplained silence crackling through a pilot's headset over the open Pacific, is where our story begins. Not with disaster, not with a blackout, not with a Hollywood apocalypse, but with silence. Because the most profound threats to modern civilization don't always announce themselves with fire and explosion. Sometimes they arrive as silence. Sometimes they arrive as light. This is the story of what happened to our sun in 2026. What it means for the planet we call home. And why the most important question we can ask is not whether a catastrophic solar storm will happen, but whether we will be ready when it does. Let's start with something that most people don't know. Something that, once you understand it, will permanently change the way you look at the sky. The sun is not a stable object. I know that sounds strange. We talk about the sun the way we talk about furniture. It's always there, dependable, fixed. Every morning it rises in the east, every evening it sets in the west. And in between it warms our fields and powers our solar panels and gives us vitamin D. We take it for granted in the way that only something truly powerful can be taken for granted. But the sun is not furniture. The sun is a thermonuclear reactor 4 times larger than the distance between the Earth and the Moon, containing 99.86% of all the mass in the solar system. It generates energy by fusing 600 million tons of hydrogen every single second. It has a surface temperature of 10,000 degrees Fahrenheit. And it has a corona, an outer atmosphere that, for reasons scientists still debate, burns at temperatures approaching 2 million degrees. 2 million degrees. That's nearly 200 times hotter than the visible surface beneath it. And embedded within that corona, threaded through it like invisible lightning, is the sun's magnetic field. A magnetic field so complex, so dynamic, so unstable, that it creates the single most energetic phenomenon in the solar system short of a supernova. We call it a solar flare. A solar flare is not a small thing. I want you to abandon whatever mental image you have right now. The little flickering flame, the small burst of light. A solar flare is an explosion. A single moderate flare releases more energy than all of the nuclear weapons ever built on this planet, detonated simultaneously. An X-class flare, the most powerful category, releases the equivalent of 1 billion hydrogen bombs going off at the same time. And in 2026, the sun did not give us one of those. It gave us dozens. To understand why 2026 became the year the sun woke up and decided to remind us who was in charge, you need to understand something called the solar cycle. The sun operates on an approximately 11-year rhythm. Scientists call it the solar cycle, and it refers to the gradual increase and decrease of solar activity, measured primarily by the number of sunspots, those dark magnetic blotches on the sun's surface that serve as the staging grounds for flares. At solar minimum, the sun is relatively quiet. Sunspots are rare. Flares are modest. Space weather, as it's called, is manageable. But at solar maximum, everything changes. We are living through solar cycle 25. It began in December 2019, when the sun's activity reached its last minimum and began climbing again. NASA and NOAA predicted it would be an average cycle, nothing remarkable, they said. Nothing to write home about. But the sun, as it turns out, doesn't care much for human predictions. Solar cycle 25 overperformed. Dramatically. By 2024, scientists were already revising their forecasts upward. The cycle peaked earlier than expected, hit higher activity levels than projected, and produced a string of X-class flares that began reminding a generation of scientists and engineers what an active sun actually looks like. And then came 2026. By early 2026, the sun was past its absolute peak. But in the world of solar physics, past peak does not mean calming down. Think of it like a hurricane that has made landfall. The center may have passed, but the outer bands are still spinning. Active regions on the Sun, those clusters of magnetically tortured plasma, were still erupting with extraordinary regularity. And one region in particular was about to write itself into the record books. Active region 4366. That is the clinical designation, the scientific name. But to the researchers who watched it in real time through the eyes of NASA's Solar Dynamics Observatory, a spacecraft the size of a school bus in geosynchronous orbit, staring at the Sun 24 hours a day, 7 days a week, active region 4366 looked like something alive, something angry. It was classified as Beta Gamma Delta. That's the most dangerous magnetic configuration a sunspot group can have. It means the magnetic field lines are twisted, compressed, overlapping, like a ball of charged wire pulled in a dozen different directions simultaneously. When a region like that releases its tension, it doesn't simmer. It explodes. And on February 1st, 2026, it did. The first flare of the day hit at 12:33 Universal Time Coordinated, an X 1.0, strong enough to cause radio blackouts, strong enough to make the instruments at NOAA's Space Weather Prediction Center in Boulder, Colorado, jump to attention, strong enough in the old days to knock out telegraph systems across a continent. But X 1.0 was just the opening act. By 12:50 Universal Time Coordinated, the region fired again, an M5.8, then another, then another. The Sun was not launching isolated bursts. It was mounting a sustained assault. Throughout the day, flare after flare erupted from region 4366, each one lighting up the X-ray sensors on the GOES 19 weather satellite in Earth orbit. And then, at 23:57 Universal Time Coordinated, just 3 minutes before midnight, the region reached into its deepest reserves and unleashed something that made every detector in the solar physics community spike to its limit. X8.1. An X8.1 class solar flare. In the scale of solar flares, where X1 is already extraordinary, X5 is catastrophic in impact, and X10 is the kind of event you write papers about for decades, X8.1 is the stuff of scientific awe. It was the most powerful flare recorded in 2026 at that point. It was one of the 20 most powerful solar flares observed since scientists began keeping systematic records in 1996. NASA's Solar Dynamics Observatory captured it in extreme ultraviolet light, a blinding golden eruption against the dark disk of the Sun, a burst of energy so vast that if you could stretch it out into heat, it would boil every ocean on Earth. Radio communications across the sunlit side of Earth, the South Pacific, Australia, New Zealand, Southeast Asia went dark. Not metaphorically dark, actually literally functionally dark. Shortwave radio, the frequency that aviation and maritime navigation depends on in remote areas, failed across frequencies below 10 megahertz. For more than an hour, pilots flying over some of the most remote ocean in the world had no radio contact with the ground. That's the pilot I mentioned at the beginning. That's his silence. And this was just the beginning, because with an X8.1 flare comes something potentially even more dangerous than the flare itself. A coronal mass ejection. Here is where I need you to slow down and really think about what I'm about to tell you, because this is the part that matters most for life on Earth. When a solar flare erupts, it sends electromagnetic radiation, X-rays, ultraviolet light, traveling at the speed of light. That radiation takes 8 minutes to reach Earth. 8 minutes. The same time it takes light from the Sun to reach us on a normal day. By the time you notice a flare happened, the radiation has already arrived. But the flare also does something else. And in the case of the most powerful eruptions, it almost always does, launch a massive bubble of magnetized plasma off the surface of the Sun. A coronal mass ejection, a CME, 1 billion tons of charged particles moving at millions of miles per hour, flung into interplanetary space like a cannon firing a continent. A CME is not fast like light. A CME is fast the way a bullet is fast, blindingly, devastatingly fast by human standards, but still bound by the physics of matter moving through space. A typical CME takes 1 to 3 days to reach Earth. A fast CME, energized by a particularly powerful flare, can make the 93 million mile trip in under 18 hours. The CME from the February 1st X8.1 eruption was launched directly, or nearly directly, at Earth. Scientists at NASA's Jet Propulsion Laboratory and NOAA's Space Weather Prediction Center immediately began modeling its trajectory, its speed, its likely impact time. And what they calculated was sobering. The cloud of magnetized plasma racing toward us was dense. It was fast. And if the orientation of its magnetic field was aligned in a specific, particularly unfortunate direction south, it would have the maximum possible impact on Earth's magnetosphere. That orientation is called southward BZ, and it is, in the language of space weather forecasting, the nightmare scenario. Here's why. Earth is wrapped in its own magnetic field, the magnetosphere, which acts as a planetary shield against the constant stream of solar particles. Under normal conditions, this shield deflects the solar wind gracefully, channeling particles toward the poles where they create the northern and southern lights. But when a CME arrives carrying its own southward-pointing magnetic field, something dramatic happens. The field from the CME connects to Earth's field in a process called magnetic reconnection. The shield, in effect, gets overwhelmed.
Solar particle pour trou.
And the energy that rains down on Earth's magnetosphere gets injected into the upper atmosphere, flowing along magnetic field lines, reaching into the very cables and wires of human civilization. The CME from February 1st struck Earth on February 4th and 5th, 2026. And while it arrived at a slight angle, grazing Earth's magnetosphere rather than hitting it dead center, the resulting geomagnetic storm still registered at KP equals 5, the threshold for what NOAA classifies as a minor to moderate event. But here's the thing about minor. In the language of space weather, minor can still knock out radio systems used by airplanes flying polar routes. Minor can still cause voltage fluctuations in power grid transformers across Canada and northern Europe. Minor can still pull the orbit of every satellite in low Earth orbit downward by measurable kilometers in a single night, dramatically increasing the risk of collision among the thousands of active spacecraft and the tens of thousands of pieces of debris already crowding our orbital environment. Minor is not nothing, and February was only the beginning, because the sun was not done with us. In the weeks and months that followed, the story of Solar Cycle 25's declining phase, if declining even deserves that word, continued to unfold with the kind of relentless energy that makes solar physicists simultaneously grateful for the data and quietly terrified of what it implies. January had already opened 2026 with a bang. On January 18th, active region 4341 erupted with an X-1.9 class flare. Powerful enough to ionize Earth's atmosphere over the Americas, powerful enough to cause a shortwave radio blackout lasting more than an hour across South America. The associated CME was a full halo ejection, meaning it expanded in every direction, including directly toward Earth. NASA's WSA-Enlil model, the primary tool used to forecast CME arrivals, tracked it at extraordinary speed. That CME hit Earth on January 19, 2026, striking at 2:38 in the afternoon Eastern Time. The geomagnetic storm it triggered rapidly escalated to G4, severe, faster than forecasters initially predicted. G4 means significant power grid irregularities are possible. It means spacecraft operations become abnormal. It means satellite surface charging can cause electronics to fail. It means high-frequency radio is interrupted across large portions of Earth. And the northern lights? They appeared over northern California. They glowed above Alabama and Mississippi. They lit up the sky over places that hadn't seen the aurora since the Carrington Event's last great echoes, over a century ago. For most people, it was beautiful. For the engineers managing critical infrastructure, the power grid operators in Quebec and Minnesota, the satellite controllers at government agencies and private aerospace companies, the aviation authorities routing transcontinental flights, it was a reminder. A warning shot. March brought more. An X-4.2 flare knocked out radio signals across Africa and Europe. April saw sustained high activity with multiple M-class eruptions from two simultaneously volatile active regions, 4420 and 4425, both carrying beta-gamma-delta magnetic configurations, both firing M-class flares at a rate that would have been considered a once-a-decade occurrence in previous solar cycles. And through all of it, the Space Weather Prediction Center issued alerts, and the world largely went on. The planes kept flying. The power mostly stayed on. The internet, for the most part, continued to function. But here is the question that haunts every serious scientist who studies space weather. What if it had been worse? What if, instead of X8.1, we'd gotten X20? What if the CME had been aimed dead center, carrying southward BZ, moving at 3,000 kilometers per second instead of 1,500? What if it had hit during a period when Earth's geomagnetic shield was already weakened? What if we hadn't had the 17 hours of warning that the January CME provided? Those questions are not hypothetical. They are historically documented. They have happened before. And the terrifying reality is that compared to what the sun is capable of, everything that happened in 2026, impressive as it was, is a moderate Tuesday. Let me take you somewhere else. Somewhere that exists only in the historical record, preserved in newspaper archives and the magnetic memories of rock samples and Antarctic ice cores. September 1st, 1859. A British amateur astronomer named Richard Carrington was doing what he did every clear morning, sketching sunspots through his telescope and projecting the image onto paper. He had been observing a particularly complex group of sunspots when, at 11:18 in the morning, something happened that he had never seen before and would never see again. The region suddenly blazed with white light. Brilliant, blinding, unprecedented white light emanating directly from the solar surface, visible to the naked eye in broad daylight. Carrington watched for 5 minutes, then ran to get a witness. By the time he returned, the light had already begun to fade. He had witnessed, for the first time in recorded human history, a solar flare observed with the naked eye. 17 hours later, the coronal mass ejection hit Earth. What happened next was, by the standards of 1859 technology, devastating. Telegraph systems across North America and Europe failed simultaneously. Telegraph operators reported receiving electrical shocks from their equipment. Some stations reported that the lines were so energized by the geomagnetic disturbance that they could send and receive messages without even connecting the batteries. The storm itself was providing the current. The northern lights were visible as far south as Cuba, as far south as Hawaii, as far south as Rome. In the Rocky Mountains, gold miners woke up in the middle of the night convinced it was dawn. In Boston, people read newspapers by the light of the aurora alone. That was the Carrington Event, a geomagnetic storm so powerful that even 165 years later, it remains the benchmark against which all space weather events are measured. And modern estimates of its magnitude, based on the magnetometer readings from the few observatories that existed at the time, corroborated by nitrate deposits in Greenland ice cores, suggest that it was a storm somewhere between 10 and 100 times more powerful than the largest geomagnetic storm recorded in the satellite era. Now ask yourself this question. What would the Carrington Event do to the world of 2026? Let's be specific. Let's be precise. Because this is not a thought experiment for the faint of heart, but it is a necessary one. In the United States alone, there are approximately 2,000 extra high-voltage transformers that form the backbone of the national electrical grid. These are not consumer electronics. They are massive, custom-built pieces of equipment, some of them as large as a house, weighing hundreds of tons, manufactured by a small number of specialized facilities, and requiring up to 2 years and tens of millions of dollars to build. The United States keeps a strategic reserve of exactly 45 of them. During a Carrington-level geomagnetic storm, geomagnetically induced currents, the electrical cousins of the aurora, flow through the ground and enter the power grid through every buried cable, every grounding wire, every transformer connected to Earth. These currents are not alternating current, the kind the grid is designed to handle. They are direct current. And when DC flows through a transformer designed for AC, the transformer heats up, saturates, and in a worst-case scenario, it fails permanently. A 2008 study commissioned by the National Academy of Sciences estimated that a Carrington-level event could destroy between 130 and 300 high-voltage transformers in the U.S. alone, causing a power outage affecting 130 million Americans. The study estimated the economic impact at $1 to $2 trillion in the first year alone, dwarfing the damage from any natural disaster in American history. And it estimated that restoration could take between 4 and 10 years. Read that again. 4 to 10 years. Without electricity, water pumping stations fail. Refrigeration fails. Hospital backup generators run out of fuel within days. Food supply chains collapse within weeks. Heating and cooling systems go silent. And in a world that has grown exponentially more dependent on electrical infrastructure since 2008, where everything from electric vehicles to data centers to telecommunications runs on power, the cascading effects would be almost incomprehensible. Now, a Carrington-level event did not happen in 2026. The storms of 2026 were serious, they were significant, they were real, but they were not Carrington scale. And yet, they still caused measurable disruptions. They still silenced pilots over the Pacific. They still triggered alarms in control rooms from Moscow to Minneapolis. They still degraded satellite orbits and interrupted aviation frequencies and generated enough geomagnetically induced current in power grid substations that operators had to manually adjust their systems to compensate. What 2026 gave us was not the catastrophe. What 2026 gave us was the preview. But before we go any further into the catastrophe that could be, let me give you something equally important and perhaps more surprising. The catastrophe that almost was. July 23, 2012. The Sun fired one of the most powerful coronal mass ejections in recorded history. Scientists later estimated it was comparable in energy to the Carrington Event, possibly exceeding it. It launched off the Sun at roughly 3,000 kilometers per second. It was dense. It was fast. It carried southward BZ, the nightmare orientation, and it missed Earth by 9 days. 9 days, the time it took Earth in its orbit to move out of the direct path of that apocalyptic plasma cloud. If the eruption had occurred 9 days earlier, the CME would have been aimed directly at us. Researchers at the University of California, Berkeley, who published their analysis in the journal Space Weather in 2014, concluded that the probability of a Carrington-level or worse event hitting Earth in any given decade is somewhere between 10 and 12%. 10 to 12% per decade. That is not a remote, theoretical risk. That is the kind of risk that actuaries build models around. That is the kind of risk that insurance companies refuse to cover. That is the kind of risk that, if it applied to bridges or airplanes or nuclear reactors, would result in immediate regulatory action and multi-billion-dollar mitigation programs. And yet, for most of history, we watched the Sun with instruments, tracked its storms with models, issued alerts in scientific language that never quite crossed the threshold into public consciousness, and hoped for the best. That is changing. What happened in 2026, the cluster of powerful flares, the G4 geomagnetic storm in January, the X8.1 eruption in February, the sustained high activity throughout the spring is changing it. Not because any single event crossed a catastrophic threshold, but because the accumulation of events made it undeniably, unavoidably clear. The Sun is active. The infrastructure is vulnerable. And the gap between what we know and what we're prepared for is enormous. Here is something I find both beautiful and troubling about human civilization. We are extraordinarily good at building things. We are extraordinarily bad at protecting them. We build power grids that span continents, linking billions of people into a shared electrical community, and we don't harden the transformers at the center of those grids against geomagnetic-induced currents, a known, documented, measurable threat. We launch thousands of satellites into orbit, creating a global nervous system for communication, navigation, and observation, and we do not fully account for the way a powerful geomagnetic storm will drag those satellites downward, compressing orbits, increasing atmospheric drag in the thermosphere as it superheats during a storm, potentially causing satellites to re-enter years ahead of schedule. We build aviation systems that depend on high-frequency radio for communication with aircraft over the poles and oceans, and we route thousands of flights every day over exactly those regions where radio blackouts are worst during solar events. We create financial systems that run on satellite-based timing signals, the kind of timing that the GPS network provides, and we don't always have backup systems in place for when those timing signals degrade or disappear during a geomagnetic storm. And we build internet infrastructure with critical nodes housed in data centers whose backup power systems are designed to handle outages measured in hours, not the days or weeks that a major grid disruption might last. In 2026, the Sun gave us a stress test, not a catastrophic one, not even close to the worst it can produce, but a genuine, sustained, multi-month stress test. And the results were instructive. Let's go through them. Aviation took the first, most visible hit. During the January and February events, polar routes, those great circle flight paths that carry aircraft from North America to Europe and Asia across the Arctic, shaving hours off intercontinental journeys, were disrupted repeatedly. High-frequency radio, which is the primary communication method for aircraft over polar regions and remote ocean areas where VHF line-of-sight radio doesn't reach, failed during the worst of the X-class flares. Radiation from the flares ionizes the D layer of the ionosphere, the lowest layer at heights between 60 and 90 kilometers, causing HF radio waves to be absorbed rather than reflected. When HF radio fails over the poles, the FAA and its international equivalents have a problem. They can reroute aircraft to lower latitudes, away from the ionospheric disruption, but those routes are longer. They burn more fuel, they cost more money, and during periods of sustained high activity, like the prolonged active phase of early 2026, the disruptions aren't isolated incidents. They're an ongoing operational challenge. Airlines reported dozens of route modifications in the first quarter of 2026 alone. The financial cost was measurable but not catastrophic. The operational cost, in terms of crew scheduling, fuel planning, and passenger disruption, was significant. And the safety implications, while managed, were sobering. There were periods during which some polar aircraft had reduced communication capability, relying on satellite phone as a backup rather than primary radio contact. In a Carrington-level event, satellite phones themselves would be degraded or unavailable. Aircraft over remote ocean would be flying in a communication environment not seen since the earliest days of long-haul aviation. The power grid was the second major concern. During the January 19th G4 storm, grid operators across Canada and the northern United States activated contingency protocols they had spent years developing and hoping they would never need. Geomagnetically induced currents, GICs, were detected in transmission lines and transformer connections from Minnesota to Quebec to Scandinavia. Operators manually adjusted load flows, took certain transmission elements out of service temporarily, and monitored transformer temperatures for signs of overheating. For the most part, it worked. The protocols held. The grid stayed on. But the protocols held is not the same as we're fine. What held in a G4 event, a severe but not extreme geomagnetic storm, is not guaranteed to hold in a G5. An G5 during a Carrington-level event might be a G5+, off the scale, in fact, since the KP index used to measure geomagnetic storms only runs to 9, and a Carrington event would potentially saturate it. The fundamental vulnerability of the grid to geomagnetic storms comes down to physics that was understood even in the 1960s, when the Quebec blackout of March 1989, caused by a powerful geomagnetic storm associated with the last major solar cycle, knocked out power to 6 million people for 9 hours and damaged transformers that took months to repair. That event prompted some grid hardening, some improvements to monitoring, some protocol development. But the core infrastructure, the massive, expensive, custom-built EHV transformers, remains largely unhardened in the United States and much of the rest of the world. The cost of hardening the U.S. grid against geomagnetic storms has been estimated at between $2 and $4 billion. A number that sounds large until you compare it to the $1 to $2 trillion estimated cost of a Carrington-level blackout. In 2026, the Department of Energy and FERC, the Federal Energy Regulatory Commission, renewed their calls for mandatory grid hardening standards. Grid operators themselves, after the January close call, invested in additional monitoring equipment. Some utilities began installing GIC monitoring devices in substations that previously had none. Small steps, important steps, but not yet the comprehensive, industry-wide transformation that the threat demands. Satellites tell a story that is both more technically complex and more immediately consequential than most people realize. Every day, in ways you probably don't think about, you depend on satellites. Your phone's GPS, the timing signals that synchronize financial transactions across global markets. The weather data that tells meteorologists where hurricanes are forming. The television and internet signals bouncing between continents. The navigation systems on ships and aircraft. The remote sensing data that monitors crop yields, tracks ice sheets, maps wildfires. During the 2026 active period, satellites face two distinct categories of threat. The first is direct damage from high-energy particle radiation. During major solar particle events, which accompany the most powerful flares, protons accelerated to near-relativistic speeds by the sun's magnetic explosions can penetrate spacecraft shielding and damage sensitive electronics. They can cause single-event upsets, essentially bit flips in computer memory, that require spacecraft computers to reboot. They can damage solar panels, degrading their power output permanently. They can blind optical sensors and degrade the performance of star trackers, which are how most spacecraft know which direction they're pointing. During the February 2026 events, ISRO, the Indian Space Research Organization, reported that more than 50 active Indian satellites were being monitored in real time for radiation effects. Other agencies and companies did the same. For the most part, the well-shielded spacecraft survived intact. Some older satellites reported anomalies. The details, in many cases, are not public. Satellite operators are understandably reluctant to publicize the vulnerabilities of their multi-billion-dollar assets. The second threat is atmospheric drag. During geomagnetic storms, Earth's thermosphere, the uppermost layer of the atmosphere, at altitudes between 80 and 500 kilometers, heats dramatically. When the thermosphere heats, it expands. And when it expands, it increases the density of gas at the altitudes where low Earth orbit satellites fly. More gas means more drag. More drag means satellites slow down. Satellites that slow down descend. And satellites that descend can eventually re-enter the atmosphere. This has happened before. It happened dramatically in February of 2022, when a minor geomagnetic storm caused the premature re-entry of 38 Starlink satellites that had just been launched into orbit. SpaceX lost $50 million worth of spacecraft in a single event that rated only G1, the lowest level on the geomagnetic storm scale. In 2026, with thousands of Starlink satellites in orbit and competing constellations from OneWeb, Amazon's Project Kuiper, and others adding to the population, the drag problem became acutely visible. Every G-class storm in early 2026 required satellite operators to compensate with propulsion maneuvers, burning precious fuel to maintain altitude and mission lifetime. Every storm slightly shortened the operational lifespan of every satellite in low orbit. And as orbital decay accelerated temporarily during storms, the risk of collision between closely spaced satellites increased in ways that are difficult to predict and nearly impossible to avoid in real time. The most crowded highway in human history is not a road on Earth. It is the belt of low Earth orbit between 400 and 600 kilometers altitude. And the Sun, with its X-8.1 flares and its billion-ton CMEs, is the most unpredictable traffic event that belt will ever face. There is a phenomenon that most people associate with science fiction that I want to bring firmly into the realm of documented, peer-reviewed atmospheric science. GPS can lie. Not because the satellites are malfunctioning, not because someone is jamming the signal, but because the ionosphere, the electrically charged layer of atmosphere through which GPS signals must travel, is distorted during geomagnetic storms, bending and scattering the radio waves in ways that introduce errors into position calculations. Under normal conditions, GPS accuracy is remarkable. Your phone can put you within a few meters of your actual location. But during a significant geomagnetic storm, ionospheric distortions can degrade GPS accuracy by tens of meters, or, in severe cases, make position signals temporarily unusable. For the casual driver following a map app, this is a nuisance. For an aircraft executing a precision approach to a runway in low visibility, it can be far more serious. For a ship navigating through a narrow channel. For a surveyor establishing property boundaries. For a military drone conducting an operation. In 2026, GPS degradation events were documented repeatedly. The FAA issued ground stop orders at specific airports during the worst periods of ionospheric disturbance, preventing aircraft from attempting precision GPS approaches until conditions improved. The Coast Guard issued navigation warnings. Surveyors in affected regions reported that instruments they had relied on for years were giving them readings that simply didn't make sense. And here is the subtler, darker problem with GPS disruption. It's not just navigation that runs on GPS. The world's financial system does. The global banking and trading infrastructure relies on GPS timing, not for location, but for the precisely synchronized timestamps that sequence financial transactions across networks. The transactions themselves are not sent by GPS. They travel through fiber optic cables and internet infrastructure. But the timing that coordinates and verifies them, the nanosecond precision that keeps the system from creating duplicate transactions or processing them out of order, comes from GPS satellites. During significant ionospheric disturbances in early 2026, financial institutions with sophisticated space weather monitoring programs activated backup timing systems, internal atomic clocks, alternative timing services, redundant protocols. Most did this quietly, without public acknowledgement. The markets kept functioning. The trades kept clearing. But the question of what would happen in a scenario where those backup systems weren't available, or where the disturbance was severe enough to overwhelm even the redundant systems, is a question that financial regulators, central banks, and infrastructure planners have been discussing with increasing urgency since the January events. Let me tell you about something that science has known for a while, but that public conversation has been slow to absorb. The sun doesn't just affect machines. It affects biology. The evidence is not perfect. It is not the kind of clean, controlled experiment evidence that scientists love most. The human body is exquisitely complex, and isolating the specific effects of geomagnetic disturbance from the hundreds of other variables that affect health is genuinely difficult. But the accumulation of epidemiological data over decades is too consistent to ignore. Studies of cardiovascular events, heart attacks, and strokes show statistically significant clustering around periods of geomagnetic activity. A landmark study published in the New England Journal of Medicine found higher rates of hospital admissions for cardiac arrhythmias during geomagnetically disturbed days compared to quiet days. Analyses of stroke incidence in multiple countries have found similar correlations. The proposed mechanism involves the disruption of circadian rhythms, the internal biological clocks that regulate everything from hormone secretion to blood pressure variation, by changes in the extremely low-frequency electromagnetic environment during geomagnetic storms. There is also evidence that geomagnetic activity affects melatonin production, which in turn affects sleep quality, immune function, and cardiovascular rhythm. For most healthy people, these effects are subtle. A slightly worse night's sleep, a mild headache, the kind of physiological fluctuation that you attribute to stress or diet and never think about again. But for people with pre-existing cardiovascular conditions, for the elderly, for those whose bodies are already operating near the edge of their physiological reserve, the cumulative effect of a sustained period of geomagnetic activity may be measurable. In the weeks following the January and February 2026 storms, researchers in several countries began pulling emergency room data, looking for signals in the noise. The preliminary results, which have not yet been published in peer-reviewed journals at the time of this writing, suggest small but potentially statistically significant elevations in cardiac event rates in affected regions. Not dramatic, not the kind of thing that would appear in a headline unless you were specifically looking for it. But in medicine, small numbers can represent large populations. A 1% increase in cardiac events across a metropolitan area during a geomagnetic storm is not a small number of people. There is something I want to be very precise about, because I think the public conversation about solar storms often collapses into two equally unhelpful modes. The first mode is dismissiveness. The sun does this all the time. The Earth survived the Carrington Event. We'll be fine. This mode ignores the fundamental transformation of human civilization that has occurred since 1859. In 1859, there were no power grids to fail, no satellites to deorbit, no GPS systems to degrade, no financial systems synchronized by atomic clocks, no aviation systems routing 100,000 flights a day. The world of 1859 was disrupted by the Carrington Event. The world of 2026 would be catastrophically, existentially disrupted by a comparable event. Dismissiveness is not rationality. Dismissiveness is willful blindness. The second mode is apocalypticism. A solar storm will destroy civilization. We have no hope. This mode ignores the enormous amount of knowledge, preparation, warning capability, and engineering resilience that does exist. We are not helpless. We have NOAA's Space Weather Prediction Center issuing alerts. We have NASA's Solar Observation Fleet, ACE, SCAVR, and a dozen other spacecraft monitoring the sun and the solar wind continuously. We have grid operators with contingency protocols. We have satellite operators with safe mode procedures. We have aviation authorities with rerouting capabilities. The G4 storm in January 2026 did not cause a grid collapse. partly because the protocols worked and partly because the storm, though severe, was not at Carrington levels. We are not helpless. What we are is unprepared for the worst case. And the worst case, while not inevitable on any given day, is not improbable across civilizational timescales. That is the precise truth, and it deserves to be held precisely. Let me tell you about the one thing that could change everything. Warning time. When a CME launches from the Sun, we have 1 to 3 days before it arrives at Earth. That seems like a lot. In some ways, it is. In other ways, it is barely enough. During the January 2026 event, NOAA's models predicted the CME arrival within a few hours of its actual impact time. A remarkable achievement of computational space weather forecasting. That warning allowed grid operators to begin precautionary measures. It allowed satellite operators to put spacecraft into safe modes, protecting their most sensitive electronics. It allowed airlines to begin rerouting plans. It allowed emergency managers to preposition resources. But here's the problem. The single most important piece of information for predicting a CME's impact, the orientation of its magnetic field, particularly whether it carries that dangerous southward BZ, cannot be measured until the CME is approximately 1.5 million kilometers from Earth. At a typical CME speed, that gives you between 30 minutes and an hour of lead time before impact. 30 minutes, 1 hour. That is not enough time to take a large urban transformer offline safely. It is barely enough time to put a satellite into safe mode. It is enough time to alert pilots and grid operators that impact is imminent, but not enough time to make the deeper structural adjustments that would truly protect the grid from a worst-case impact. This is the gap that space weather scientists have identified as the highest priority problem in the field. And in the wake of the 2026 events, there is renewed urgency around the development of a new generation of space weather monitors, spacecraft positioned not at the L1 Lagrange point, where Discover currently sits 1.5 million kilometers from Earth, but at greater distances from the Sun, where earlier warning could be provided. ESA has a mission called Vigil, also known as the Lagrange mission, that would place a spacecraft at the L5 point, trailing Earth in its orbit, with a view of the Sun's far side that allows earlier detection of sunspot regions before they rotate into Earth-facing position. The mission could provide up to 2 weeks of additional warning of developing active regions, not warning of CME impact, but warning that a dangerous region is coming. And there are proposals under active development in both government and private research for spacecraft positioned further from Earth along the Sun-Earth line, what scientists call a solar shield concept, that could provide hours of additional southward BZ warning, potentially transforming the grid protection calculus entirely. These are not science fiction. They are engineering programs with budgets and timelines and technical teams. What they need is political will and consistent funding. The two things that space weather preparedness has historically struggled most to attract, precisely because the threat is rare enough that each new administration is tempted to defer it as someone else's problem. The events of 2026 have not created that political will. Not yet, but they have made the conversation harder to avoid. Let me take you somewhere that few people consider when they think about solar storms. Somewhere that reveals just how deep the sun's reach extends into modern life.
Agriculture.
In the spring of 2026, farmers across North America and Europe were using precision agriculture systems, satellite-guided tractors that follow GPS-derived routes to within centimeters, optimizing seed placement, fertilizer application, and irrigation with algorithmic precision. These systems have transformed farming over the past decade, allowing smaller operations to manage more land with fewer people, reducing waste and environmental impact, increasing yields. During periods of significant GPS degradation in early 2026, some of these precision agriculture systems simply stopped working as designed. Tractors that were supposed to follow tracks within 2 centimeters were drifting by meters. Automated systems that were supposed to apply variable rate fertilizer based on GPS coordinates were unable to geolocate with sufficient precision. In some cases, farmers manually disengaged the automated systems and reverted to less efficient traditional methods for the duration of the disruption. It was a manageable inconvenience in 2026. In a longer, more severe disruption during a critical planting or harvesting window, the economic impact on food production could be substantial. Then there is the power question. Modern agricultural operations are electricity intensive. Irrigation pumps, climate-controlled storage facilities, grain dryers, feed systems for large-scale livestock operations, a prolonged power grid disruption during a critical agricultural period, during a summer drought when irrigation is already maxed out, for example, could cause crop losses that ripple through food supply chains in ways that extend far beyond the initial storm. None of this happened in 2026. But every agricultural planner with a sophisticated risk management framework has it on their radar now. And then there is the thing that most of us carry in our pocket, your smartphone. In 2026, the global smartphone is no longer just a communications device. It is the interface through which billions of people access banking, medical records, navigation, social coordination, news, work. It is the remote control for smart homes. It is the point-of-sale terminal for businesses that have abandoned cash. It is the digital wallet, the boarding pass, the health monitor, the emergency alert receiver. The smartphone itself, the physical device in your pocket, is unlikely to be damaged by a geomagnetic storm. It has no long conductors to serve as antennas for geomagnetically induced currents. It's not connected to the ground. It's essentially a sealed, portable electronic device that is reasonably well insulated from the direct effects of geomagnetic disturbance. But the smartphone is useless without the network. And the network, the cellular towers, the fiber optic backbones, the data centers, the cable landing stations that link continents, the DNS servers that translate URLs into IP addresses, the GPS satellites that synchronize everything, the network is not insulated. The network is deeply structurally vulnerable. A major geomagnetic storm doesn't need to physically destroy the infrastructure to make your smartphone useless. It just needs to knock out power in the right places. It just needs to degrade GPS timing signals enough to desynchronize network operations. It just needs to damage enough high-altitude telecommunications satellites to remove the redundancy that keeps internet traffic flowing when terrestrial cables fail. During the January 2026 storm, internet performance across some northern regions showed measurable degradation. Not failure, degradation, latency spikes, packet loss, the kind of performance issues that, in a normal situation, would be attributed to network congestion or a routine equipment problem. But monitoring systems specifically designed to track space weather effects on internet infrastructure confirmed the correlation. In a Carrington-level event, the degradation becomes something else entirely. The economic analysis firm Lloyd's of London estimated, in a widely cited 2013 report, that a Carrington-level geomagnetic storm affecting the United States would cause between $0.6 and $2.6 trillion in economic damage in the first year alone, primarily through power grid disruption and the cascading effects on every sector of the economy that depends on electricity. That estimate, written before the explosion of cloud computing, before the mass electrification of transportation, before the widespread adoption of electric heat pumps, before the proliferation of satellite-dependent precision agriculture, that estimate is almost certainly too low for 2026. The economy has become more electricity-dependent, not less, in the intervening years. The threat has grown as the infrastructure has grown. But I don't want to leave you in darkness, metaphorical or otherwise, because alongside the vulnerabilities, there is something equally real: the remarkable human capacity for innovation when confronted with existential challenges. Space weather forecasting in 2026 is incomparably better than it was 20 years ago. NOAA's Space Weather Prediction Center issues forecasts that cover a range of solar activity with skill levels that were simply not achievable a decade ago. Machine learning algorithms trained on decades of solar observation data now assist human forecasters in identifying dangerous active regions and predicting CME trajectories. The ACE and SCAVR spacecraft at L1 provide a constant stream of in-situ solar wind measurements that feed into the models. Grid resilience programs, while not yet comprehensive, have made real progress. NERC, the North American Electric Reliability Corporation, has issued standards requiring utilities to assess and mitigate their geomagnetic storm vulnerability. Some utilities have installed GIC blocking devices on key transformers, essentially capacitors that allow the AC power to flow normally while blocking the DC geomagnetically induced currents that cause transformer heating. The technology works. It exists. The question is deployment scale and speed. Satellite resilience has improved as well. Modern spacecraft are designed with radiation-hardened electronics. components specifically engineered to withstand the energetic particle environments that accompany major solar events. Safe mode procedures are now standard practice, allowing ground controllers to put a satellite into a protective minimal function state during a storm, then restore full operations after conditions improve. Even in aviation, the development of alternative position and navigation systems that don't rely solely on GPS, has accelerated. The FAA's Next-Gen Air Traffic Management Modernization Program has included provisions for GPS backup systems. ICAO, the International Civil Aviation Organization, has developed procedures for maintaining polar flight safety during HF radio outages. The picture is not one of paralysis. It is one of a civilization slowly, imperfectly, but genuinely coming to terms with a threat that operates on timescales both geological and immediate, that has been there since the sun formed 4.6 billion years ago, and that will be there long after our current civilization has been succeeded by whatever comes next. I want to pause here and make an observation that might seem strange coming in the middle of a discussion about solar storms and grid failures. The aurora borealis is one of the most beautiful things in the natural world. And in 2026, millions of people who had never seen the northern lights, who had assumed reasonably that seeing the aurora required a trip to Alaska or Iceland or Norway, looked up from their backyards in Kentucky and Tennessee and northern Spain and saw the sky on fire with curtains of green and purple and crimson light. During the January G4 storm, the aurora was visible as far south as Northern California. During subsequent storms in spring 2026, reports of aurora sightings came from cities in the American Midwest that hadn't experienced visible aurora in living memory. Social media was flooded with photographs, amateur astrophotography of extraordinary quality, capturing the shimmering, shifting curtains of light against dark suburban skies. For a brief moment, the sun reminded us that it is not only a threat. It is a spectacle. It is the closest star. It is the source of every joule of energy in the food on your plate, the coal or gas in your power station, the oil in your fuel tank. All of it stored solar energy from millions or billions of years ago. The sun created the conditions for life on Earth. It sculpts the heliosphere, the enormous bubble of solar wind that surrounds the entire solar system, shielding us from the cosmic radiation of interstellar space. The aurora is what happens when the sun reaches out and touches Earth's atmosphere directly, when the magnetic field lets some of those solar particles through to the polar regions, where they collide with oxygen and nitrogen atoms and excite them into glowing. Green from oxygen at 60 to 150 miles altitude, red from oxygen at higher altitudes, blue and purple from nitrogen. The palette of the aurora is the electromagnetic signature of our own atmosphere, illuminated by the sun's energy. People who saw the aurora in January 2026, many of them for the first time, reported something that I think is important to record. They reported a feeling of connection, of insignificance in the best possible sense, the kind of insignificance that comes from suddenly apprehending your actual place in a cosmos that is incomprehensibly large and incomprehensibly beautiful. Science can give you that. The sun gives you that. Let's talk about what's likely coming. Not as prophecy, the sun is notoriously difficult to forecast on specific timescales, but as informed probability. Solar cycle 25 is past its peak, but not its danger. The declining phase of a solar cycle is not a smooth, gentle wind down. It is erratic. Individual active regions can still produce X-class flares and powerful CMEs even as the overall sunspot count decreases. Some of the most significant geomagnetic storms in history have occurred in the declining phase of solar cycles, when the magnetic configuration of the sun can produce particularly geoeffective CMEs. Solar cycle 26 will begin sometime around 2030, if current predictions hold. NASA and NOAA typically make preliminary predictions about upcoming cycles based on precursor indicators, measurements of the sun's polar magnetic fields, analysis of surface flux transport patterns, statistical modeling. Early indications for cycle 26 suggest it could be stronger than cycle 25, but the scientific community is the first to acknowledge the limits of long-range solar activity prediction. What we can say with confidence is this: the sun is currently in an active state. That active state will persist for at least the next several years. During that period, significant X-class flares and powerful CMEs are not unusual occurrences. They are expected. They are part of the normal operation of a star that has been doing this for 4.6 billion years. The relevant question is not whether they will happen. The relevant question is whether, when they happen, human civilization is organized and equipped to manage the consequences. I want to take you to a room that most people never hear about. It is in Boulder, Colorado. It's at the NOAA campus, a complex of low-slung government buildings set against the backdrop of the Rocky Mountains. Inside, in a facility that operates around the clock, 365 days a year, staffed by forecasters who rotate through 8-hour shifts monitoring a wall of screens showing real-time data from every solar observation satellite and ground station in the world, is NOAA's Space Weather Prediction Center. On the morning of January 18, 2026, the forecasters in that room watched the data from the ACE spacecraft at L1 and from the GOES 19 X-ray sensors and from NASA's SDO, and they recognized what they were seeing. They had seen X-class flares before. They had modeled CMEs before. But the combination of this particular flare's intensity, the size and speed of the associated CME, and the trajectory of the ejection aimed squarely at Earth, put them on high alert. They issued an alert, a geomagnetic storm watch. A G3 strong was initially forecast. Within hours, as new model runs and additional coronagraph data refined the picture, the forecast was upgraded. G4, severe. The alerts went to power grid operators through a system that has been steadily improved over the past 15 years. They went to satellite operators. They went to aviation authorities. They went to the emergency management community. They went through automated public alert systems to media organizations that, to varying degrees depending on the news environment that day, passed them on to the public. The public, by and large, didn't panic. They also, by and large, didn't take any particular action. Most people don't have a space weather emergency kit. Most people don't know what to do when the northern lights appear over their city and the power flickers and the GPS on their phone starts giving slightly wrong directions. That is a public education gap that, in 2026, became more visible than at any time in recent memory. The storm passed. The aurora photos went viral. The news cycle moved on. But in the infrastructure world, in the national security and energy policy world, in the scientific community, the conversation continued. What would public awareness actually look like? What would a well-informed public do differently during a space weather event? Would they know to have backup communications plans? Would they understand why their GPS might be unreliable? Would they know that the power might be intentionally curtailed by grid operators taking precautionary measures, and that this is a planned, protective action, not a sign of catastrophic failure? These are questions that public science communicators, emergency managers, and science journalists have been asking with renewed urgency since early 2026. There is a diplomatic dimension to space weather that most people never consider. Geomagnetic storms don't respect borders. They don't distinguish between allied nations and adversaries. They knock out radio communications used by militaries as readily as by commercial airlines. They degrade GPS signals that guide both civilian aircraft and military systems. They cause satellite anomalies in the spacecraft of every country that has them. In the Cold War era, the geomagnetic storms of the 1970s and 1980s caused enough disruption to military communications that they triggered, on at least one documented occasion, genuine concern in command centers about whether the disruptions were natural or adversarial. The ability to correctly identify a space weather event and distinguish it from an enemy attack is not a trivial diplomatic and military capability. In 2026, with satellite-based surveillance, communication, and navigation deeply embedded in the military operations of multiple nuclear-armed states, the question of how space weather affects crisis stability is not an abstract academic concern. It is a live operational question. A scenario in which a powerful CME simultaneously degrades the early warning and communication systems of two adversarial nations at a moment of political tension is a scenario that defense analysts call a compound crisis, one in which multiple stressors interact to create risks greater than any individual component. There are international channels for space weather coordination, the International Space Environment Service, the UN Committee on the Peaceful Uses of Outer Space, bilateral scientific exchange programs. These channels have been quietly important for decades, sharing data and model forecasts that help all countries, regardless of their political relationships, manage the impacts of solar storms. In 2026, those channels worked. Forecasts were shared. Data was exchanged. Space agencies from India, Europe, Japan, and the United States coordinated satellite observations and shared information in near real time. The scientific community, whatever its governments were doing, maintained the cooperative ethos that has characterized international solar physics research for decades. That cooperation is itself a form of infrastructure, invisible, underappreciated, and critically important. Let me bring this home. Literally, what does a solar storm actually mean for you? Not for the grid, not for satellites, not for aviation, but for you specifically as a person living in a modern city or suburb in the United States in 2026. For the vast majority of people, the answer to that question, for the events that have actually occurred in 2026, is the aurora was visible from your backyard, your GPS was slightly unreliable for a few hours, and your high-frequency radio didn't work if you happened to be using one. That's it. For most people, most of the time, the storms of 2026 were awe-inspiring and scientifically significant and not personally disruptive. And that is actually the right outcome. It means the warning systems worked, the grid operators responded appropriately, the satellite operators took precautions, and the sun, while active, did not throw its absolute worst at us. But not its absolute worst is doing a lot of work in that sentence. If you want to be genuinely prepared, not paranoid, not obsessed, but practically calmly prepared for the possibility of a more severe event in the years ahead, here is what that looks like. It looks like knowing that if a major geomagnetic storm is forecast, GPS-dependent services may be unreliable. Have an old-fashioned paper map or a downloaded offline navigation app as backup. Know your route home from work without GPS. It looks like keeping some cash on hand because the electronic payment systems that GPS timing supports could be temporarily degraded. Not hundreds of dollars, just enough to handle a day or two if card payment infrastructure is temporarily unreliable. It looks like having a battery-powered or hand-crank emergency radio. If the power goes out and your internet is down and your smartphone has no signal, a simple battery radio that can receive AM and FM broadcasts is your connection to emergency information. It's also a connection that requires no satellite, no GPS, no fiber optic cable, just the oldest, most resilient broadcast technology we have. It looks like knowing the location of your nearest community resilience hub, your local emergency management office, the community center that has a backup generator, the firehouse that will be operating regardless of grid status. And it looks like having a few days' worth of supplies, water, food, medication, not because space weather is uniquely likely to create a prolonged outage, but because the same common-sense preparedness that helps in any emergency helps in this one. None of this is survivalism. None of this is paranoia. This is exactly the kind of practical, proportionate preparation that FEMA recommends for hurricane-prone or earthquake-prone regions, applied to a threat that is geographically universal, because unlike a hurricane or an earthquake, a major geomagnetic storm can affect the entire northern hemisphere simultaneously. Here is what I want you to take away from everything I have told you. The sun is alive. Not in the biological sense, it has no cells, no metabolism, no intention. But it is dynamic. It is changeable. It is active in ways that directly affect the planet it illuminates, and through that planet, every living thing and every human structure on its surface. For most of human history, we watched the sun and felt its warmth and planted by its seasons and told time by its arc across the sky. We did not depend on it in the way we now depend on it, through the invisible threads of electrical and electromagnetic infrastructure that the sun can, in its more energetic moments, reach out and tear. The events of 2026 did not break those threads, but they pulled on them, hard enough to feel, hard enough to make a generation of engineers and scientists and policymakers feel, in a visceral way that data alone cannot convey, the weight of what they are responsible for protecting. The question that solar physicists have been asking for decades, when will the next Carrington-level event occur, cannot be answered with precision. What the statistics tell us is this: it will occur. Not in a specific year, not on a specific day, but within the kind of timeframes that human civilization can and should plan for. The 12% per decade probability is not a comfort. It is a call to action. The action is already happening in Boulder, Colorado, in the control rooms of grid operators, in the clean rooms where radiation-hardened spacecraft are assembled, in the research laboratories where machine learning models are being trained on solar observation data. It is happening quietly and imperfectly, at the pace that underfunded but dedicated science and engineering communities can manage. What could make it happen faster is public attention, political will, the recognition that space weather is not a curiosity for astronomers. It is a national security issue. It is an economic issue. It is a public health issue. It is an infrastructure issue of the first order. The northern lights over Alabama in January 2026 were beautiful. They were also a warning light, glowing green and red across a winter sky. They were the sun's way of reminding us, I am here, I am active, and the infrastructure of your civilization is threaded through my magnetic domain. I want to end not with fear, but with something that I think is the appropriate emotional response to everything I've described. Wonder. Because everything I have told you, the plasma eruptions, the magnetic reconnection, the 10 million degree corona, the billion-ton clouds of charged particles racing across 93 million miles of interplanetary space. All of it is real. Not hypothetical. Not dramatized. It is the actual, documented, peer-reviewed physical reality of the star we orbit. We live in a solar system that is alive with energy and event. Every day, the sun sends a stream of charged particles past our planet. The solar wind, moving at 400 kilometers per second, carrying with it the sun's magnetic field into the reaches of the outer solar system. Every few weeks, an active region on the sun erupts and we detect it with instruments that didn't exist 30 years ago. Every few years, a storm significant enough to make headlines and fill emergency management offices with urgent conversations reminds us that the relationship between Earth and the sun is not static and safe. It is dynamic and intimate and occasionally violent. And we, this strange species that has in a geological eye blink gone from chipping flint tools to launching telescopes into space, have now built enough sensors and spacecraft and computational models to watch all of this in real time, to see the flare the moment it erupts, to track the CME as it crosses interplanetary space, to forecast with genuine skill when it will arrive and how powerful the storm will be. That is remarkable. That is one of the great scientific achievements of this era, not one with the glamour of a Mars landing or the public excitement of a gravitational wave detection, but arguably more immediately consequential than either. The stars are not passive backdrops. They are not decorations in the night sky. They are engines, vast, energetic, magnetically complex engines, and we orbit one. Every day, our power grids and satellites and GPS systems and financial networks and aviation routes and agricultural systems and smartphones, all of it exists within the magnetic sphere of influence of a star that has been active for 4.6 billion years and has at least another 5 billion to go. The least we can do, the very least, is pay attention. The sun is talking to us. In the language of X-rays and magnetic fields and billion-ton plasma clouds racing through interplanetary space. In the language of radio silence over the Pacific and aurora curtains over Alabama and satellites drifting from their orbits in the thermospheric warmth of a geomagnetic storm. In 2026, it spoke a little louder than usual. I think it's time we started listening.